Today we will see about balancing of rotating and reciprocating masses. So first we will see balancing of rotating masses. See, whenever we are having machine elements having rotating motion or reciprocating motion, there must be some centrifugal forces generated if there is any unbalanced mass present in our component. So suppose here two different examples are given. You can see the first example is whenever you are having any mass at a particular distance from the rotating axis, right? Suppose m is the mass which is rotating at a radius r from the rotational axis, right? So if that is rotating at that particular distance, it will have this centrifugal force mr omega square, and because of that there is an unbalance, right? This is one case. Another case is if the center of gravity or that particular mass center of the particular component is not on its geometric center, right? Here is the geometric center of this particular disk, but the center of mass is not coinciding with that particular geometric center. It may be because of some density difference. We all know that during casting it may happen that during solidification some of the difference in density distribution may be there, and because of that the geometric center may have a little bit eccentricity E. So because of that also you can have unbalanced force, right? That is again the centrifugal force me omega square. So this is how you can have some unbalanced forces present in rotating element. So whenever you are having this unbalanced forces or unbalanced mass present in the component, you have to balance those mass, right? So actually I will share this link when you will solve some of the numerical, right? So I will share it shortly because you don't want to waste time, right? So yes, once you got idea about this how unbalanced forces are there, then we can start with different
सर पहले वाली खोल ले एक बार स्लाइड सर इससे पहले वाली एक बार पूरा दिखाइए सर पूरा
yes, this is the full slide. It will anyway be shared with you, right, in the drive, and I will share the drive link. So it is fine if you miss some of the screenshot. You can have that full PDF at the end of this session. Okay. Hello.
Yes, sir, that's fine. Yes, sir.
Okay. Okay. Now, if we go for a balancing of this unbalanced mass, then in that case we can take different cases. So first is the static balancing. Static balancing means whenever you are having this unbalanced masses are in the same rotatory plane and you are having some unbalanced at some different radii, as it is mentioned in this given figure, that here you may have some rotating disk, and in that disk you can have some unbalanced mass m1 at radius r1, m2 at radius r2, and m3 at radius r3, right? So if you are having this unbalanced masses rotating at same velocity or same angular velocity omega, then you need to balance this particular unbalanced forces by providing a balanced mass at a particular balanced radius. MC and RC is representing balanced mass, right? And this RC is balancing radius respectively. So here basically in static balancing you need to go for only force balance, right? Because you are not having any couple generated in case of this particular case which we are discussing, that all the mass are in the same plane and they are generating unbalanced force. See, this can also be visualized by graphical method by drawing this force polygon, right? This is force polygon. So what they have done is they have this angle theta 1, so they have started with this particular starting point. This is your starting point, and here you know this angle is theta 1 as it is mentioned, right? So one second. Yeah, so we were discussing about this force polygon. So here, as I have told you, this is graphical method to solve for this balancing mass and radius. So what you need to do is first you have to draw this m1 r1. Actually, this force will be m1 r1 omega square, right? This force will be m2 r2 omega square, and here it will be m3 r3 omega square, and this will also be mc rc omega square. But while drawing force polygon, if you observe, they have taken only the product of m1 r1 m2 r2 and m3 r3 and mc rc, right, like that. Why? Because all the rotating masses are having the same angular velocity omega, so they have neglected that and they have considered only the product of mass and radius. So here what you are going to do is you are going to draw this vector at a given angle theta 1, right? So m1 r1, then the theta 2 angle is given, so from positive x direction you will take angle theta 2 and you will draw this m2 r2. You will definitely choose a suitable scale in order to draw this, right? Actually drawing this kind of polygon is not new for you. In velocity and acceleration diagram also we have seen that by taking certain suitable scale you are representing velocity of different components, right? So here also you will take some suitable scale and you will represent this m1 r1 m2 r2 and m3 r3, right, like this. If you go with this given angle and the magnitude you are getting for m1 r1 m2 r2 and m3 r3, you will find that this polygon is not being closed, and once you have this open polygon, it means there is some unbalanced force present in the system, right? This unclosed polygon will give you idea that there is some unbalanced force present in the system. So when you join that particular polygon and you will complete that polygon, so in that case you can find the value of this mcrc. So once you know the value of mcrc, you have to decide either MC or RC, or means whenever you are solving it practically, then you can decide either the balancing mass or the balancing radius, and the remaining one of them you can calculate from the product you have already achieved through this polygon, right? This is what the graphical method, right? Whatever we have discussed is graphical method, right? There is analytical method is also there. So if you want to go for analytical method, right?
सर एक बार पहले वाली स्लाइड करना सर, स्क्रीनशॉट लेना भूल गया सर मैं.
Done?
ओके सर ओके.
So once you are done with this graphical method, kindly mute yourself. Kindly mute yourself. Hello, someone is there with through. Through, kindly mute yourself. Through.
Sir, you can also mute him as you are the host.
I don't think so. Let me check. It is 1 second. Yeah. Thank you.
Yes.
Yeah. Thank you. Yes. So what is happening? Okay. Yeah. So we were,
So,
yes.
sorry, in the graphical method, how we have to find the unbalanced force?
So that is what I have told you, no? See, here you are having this M1 R1, M2 R2, and M3 R3 are nothing but representing the centrifugal force due to those unbalanced masses, right? And actually we are neglecting omega because all the masses are on the same disk and they are rotating with the same angular velocity. So if you find this unclosed polygon, right, you can close this polygon, and whatever magnitude of that particular vector, this vector is going to have certain magnitude, right, MCRC. Yes or no?
Okay.
Yes, sir.
Right, so this vector will give you that MCRC, and when you multiply it with this omega square, then you can have that particular balancing force required. And once you get this product MCRC, you can decide either balancing mass. Once you have the product MCRC with you, you can either decide balancing mass or balancing radius. One you can decide, another you can calculate. Okay. So in case of analytical method, what you have to do is, if you observe that here force is m1 r1 omega square plus m2 r2 omega square plus m3 r3 omega square, right? Here it is statically balanced, right? It means this f, whatever you have calculated, this must be 0, right? Now in our case, as we have seen, this f is not coming 0. So when this f is not coming 0, then what you have to do is this sigma f plus certain balancing force must be equal to 0. Now this sigma f is nothing but this product of m and r.
Sir, your
Means,
voice is.
hello, can you hear me?
Yes, sir, but sometimes your voice is distorted.
Okay. So here in our case there are three masses, right? So here sigma I is equal to 1 to 3 mr plus this balancing mass and radius, right? That is MCRC. It must be equal to 0. Now if you observe this figure, you are having that horizontal and vertical component, right, of each forces. This m1 r1 is acting in this direction, which is making an angle of theta 1 with x-axis. So the component along x-axis will be m1 r1 cos theta 1, and component along this y-axis, right, will be m1 r1 sin theta 1. So similarly for mass 2 and mass 3 also, it will have component m2 r2 cos theta 2 and m2 r2 sin theta 2, like that. So if you take sigma of forces acting in horizontal direction equals to 0, then you will lead with this sigma mr cos theta plus MCRC cos theta equals to 0. Again here I will be equal to 1 to 3 in our particular case, right? And similarly
Sir, is the
for
first
sigma.
equation in vector form?
Sorry?
Sir, is the first equation in vector form?
Uh, which one?
Analytical method, first equation.
This one?
No, sir, first line.
This one?
Yes,
Yeah,
yes, sir.
yes. It must be, yeah. And then that vector sum must be equal to 0 in order to get that statically balanced system. Okay.
Okay, sir.
Okay. Now here for vertical direction, sigma again I is equal to 1 to 3 mr sin theta plus mcrc sin theta must be equal to 0, right? So what happens is, here you will get the value of that mcrc cos theta. It will be minus mr cos theta. I am not writing that 1 to 3 and all, now you can understand, or 1 to n, whatever we can write as per the given problem, Right, so once you have this data with you, you can square and sum of above two equation in order to get the magnitude of this MCRC. Right, sigma mr cos theta square plus sigma mr sin theta square. Right, so here, as we have received this MCRC previously in our what you can say, that graphical method, here also you will get the value of MCRC, right? And that theta was directly available from that graphical method. Here you have to calculate this theta by taking that ratio of above equations, right? mr sin theta upon mr cos theta. Right, here while taking this angle theta c, it is important to carry the sign whatever you are getting. So whenever you are taking that summation of mr sin theta, if it is coming positive, then it should be positive only, and if it is coming negative, then it will get this negative positive. Otherwise, whatever you are getting, you have to keep it as it is, because this sign will decide, sign is going to decide the quadrant, right? So that is why you have to keep the sign as it is, right? So this is how you will calculate the balancing mass and the angle at which that balancing mass needs to be provided for statically balanced system. Now, after having this particular idea about that balancing of rotating masses, right, in the same plane, this is the simple problem given, that three masses of 8 kg, 12 kg and 15 kg attached at radial distances of 80 mm, 100 mm and 60 mm respectively to a disc on a shaft, right, are in complete balance. Now determine the angular positions of the masses of 12 kg and 15 kg relative to the 8 kg mass. 8 kg, 12 kg and 15 kg. So what here in the given data for your problem, I am giving you some hints so that you can then start solving the problem. They are telling that you are having this 8 kg, right, is at 0 degree, I guess they are considering, or we need to consider it as 0 degree, because you have to calculate the position of 12 kg and 15 kg, right, relative to 8 kg mass. So we are considering that 8 kg is lying at the x-axis, and with respect to this you have to calculate the angle for 12 kg, right? Let us say it is theta 2.
पहले वाला स्लाइड बोलना एक बार.
Hi, 1 second. And let us say this theta 3, right? This is 12 kg, let us say, and this may be 15 kg, right? So from the data given here, your theta 1 is 0, and it is told that the system is in static balance, so you need not to provide extra mass. What you need to find is, you need to just find this theta 2 and theta 3. So can you try to solve this?
Trying, sir.
Yeah, so please try and solve this. It is very simple. So let me write something over. So here what you will do is, you will have this product M1 R1 M2 R2 and M3 R3.
सर थोड़ा सा नीचे करना, थोड़ा स्लो डाउन मींस थोड़ा नीचे करना स्लाइड को.
1 second. So M1 is given as 8, right? R1 is given as 18, M2 is given as 12, R2 as 100, M3 as 15 and R3 as 16. So you will have this product as 640 and 1200, and here you will have 900. So what we have seen is that sigma mr must be equal to 0 if we go by analytical method. Then here you will have that 640 cos 0 plus 1200 cos theta 2 plus 900 cos theta 3 must be equal to 0 when you take that sigma fh is equal to 0, right? So it will give you 1200 cos theta 2 is equal to minus of 640 plus 900 cos theta 3, right? So this is from sigma fh is equal to 0. Similarly, if you will go for sigma fv is equal to 0, then you will end up with 1200 sin theta 2 is equal to minus 900 sin theta 3. There will not be any component for 640 because 640 sin 0 will be 0. So once you get this, what you can do is you can square and add above this equation, whatever two equation we have got here, right? This is equation 1, this is equation 2. So if you square and add both the equation, what you will get is you are going to get 1200 square is equal to this 640 square plus 900 square cos square theta 3 plus 2 into 640 into 90, sorry 900 cos theta 3 plus 900 sin square theta 3. So here again sin square theta 3 plus cos square theta 3 will be 1, so you will be able to find the value of cos theta 3. So from this you will have cos theta 3 equal to maybe 0.1913. So when you solve this, as here you are not having any sign when you are solving this, we have to consider both the possibility for theta 3 79 degree or 281 degree. Is anyone getting the same answer? Hello? Hello?
Yes, sir.
No,
No,
sir.
not getting that, sir.
So can you check whatever I have written? You can match it.
Yes, yes.
Yes, these two equations, right? This one and this one you need to check. These two equation if same, then you must be getting the same theta 3. Okay.
Okay, sir.
So once you get this theta 3, then you have to take both the cases. First case will be theta 3 with 79 degrees and 79 degree angle. If you proceed further, then what you will end up with is theta 2 equals to 227.4. Here also you will have some more options, but as you know that our both the what we can say that here both the values of this this theta 2 is in negative, so when both are negative, then it must be the third quadrant, right? So that is why this theta 2 is taken in the third quadrant. Similarly, if you will go for this theta 3 is equal to 281 degree, then you will find that theta 2 will be 132.6 degree. So this is how you will be able to calculate the balancing masses and the location at which these balancing masses are there, right? So this is how you can calculate this. So is it clear?
Yes, sir. Yes, sir.
Okay. So now if we go for the next one, that is the dynamic balancing. So previously what was the sorry? Hello. So previously whatever we have seen in that, actually if you take this disc are having those whatever number of mass at a particular angle and what we can say distance, right? So it is the same plane, right?
Yes, sir.
Right, but here in dynamic balancing what happens is, in addition to the force, you
Sorry
will
for
also,
interrupting, sir.
yes, yes,
How could it be the same plane? Because the quadrant are different.
quadrant are different but plane is same, na? What is
Oh,
plane?
uh,
Huh,
uh,
okay.
okay, sir. Okay.
Yeah, so in case of this dynamic balancing, in addition to force, the couple generated because of this unbalanced force, couple also must be in equilibrium, right? Then also you can achieve the dynamic balancing, right? So first, previously we have only this requirement that sigma mr is 0. Now one more condition needs to be satisfied, and that is sigma mr l must be 0, because here as you can see, this m1 r1 omega square and m2 r2 omega square both may be having the same magnitude m1 and m2 and lying at the same distance, maybe r1 and r2. So it can nullify that force, right, in the opposite direction. But what happens is they are going to generate a couple. Right, they are going to generate a couple that mr omega square into L. So in case of dynamic balancing, this couple which is generated due to this opposite forces, that must be nullified, or that must be balanced, right? So in case of dynamic balancing, in addition to force, you also have to take care of the unbalanced couple, right? So now we will see how we will do that. So that is there in this particular case of this balancing of several masses in different plane. So
सर एक बार कर दो सर
actually you will be having this PDF, right? So if you miss one or two, that's screenshot, that is
स्टार्ट करना एक बार जिसमें डायनेमिक बैलेंसिंग था
okay. Okay, can we go ahead? Hello? Hello?
Yes, sir. We don't have problem. So
Okay.
you can go ahead.
Okay. Yeah. So here, as in case of this balancing of several masses in different plane, you can see here there are different masses like m1, m2 and m3, and now they are not on the same rotor, they are on the different rotor, right? So here you are given this plane 1, 2 and 3, in which you are having that mass at a particular angle, right? In each plane you are given this mass and angle and the distance at which that unbalanced mass is there. So once you have this kind of situation, what you are going to do is you are going to take two different planes like C1 and C2, right? So in this C1 and C2, what you are going to do is you are going to provide two more masses for balancing, right? This MC1 and MC2. So here for plane C1 you will have MC1 at a radius RC1 and at an angle theta C1. Similarly, in plane C2, you will find that MC2 is the required mass at required radius RC2 and at an angle theta C2. So here also, if first we see the graphical method, then it is easy, right? In graphical method, as you can see, here you will have force polygon as well as couple polygon, right? So this whatever distance is also there, right, in this polygon, that is couple polygon. And here only this product of M and R is there, that is force polygon, which we have seen earlier also. So what is done here is first they have taken this C1 as a reference plane, as you can see. So with reference to this plane, the moment generated or couple generated of all the forces are considered, like M1, R1, L1, M2, R2, L2, M3, R3, L3, like that. and they have started drawing this polygon, right, M1 R1 L1 at an angle theta 1, which is provided here. You can see that here this theta 1, right. Similarly, then at angle theta 2, M2 R2 L2. Similarly, at angle theta 3, M3 R3 L3. So this is how you are having again this couple polygon, and you can see again couple polygon is also unclosed. So you can close this couple polygon, right? So when you close this couple polygon, you will find that the magnitude of this particular vector will be equal to MC2 RC2 LC2, and angle will also be there with you like this theta C2. So when you draw this couple polygon, you will have magnitude of this MC2 RC2 LC2, and angle you will also find that theta C2. So here, while you are balancing this several masses in different plane, again you will decide previously that at what particular distance you are taking this plane in which you are going to provide your mass. So this LC2 is anyway will be decided by you. So then again the product of MC and RC has come, right? So previously, as we were used to decide one of them and calculate the others, here also you will do the same. So by solving this couple polygon, you will have your balancing mass required in plane C2, MC2 and RC2, right? Now once you have MC2, RC2 with you, what you can do is you can draw this fourth polygon, right, because you don't know what is the mass required in plane C1, right? So for that you have to again start with this M1 R1 at an angle this theta 1, as you have seen in that couple polygon. The same procedure you will follow, but here you will consider the magnitude of force, right? So that is why it is known as force polygon. Again here it will be an unclosed force polygon, and when you are going to close it, you will find the magnitude of this MC1 RC1, and from that you can decide again that either you can decide the radius at which you want to provide balancing mass, so you can calculate magnitude of mass, and if you decide the magnitude of that balancing mass, then you can decide at which radius it is required to provide. So this is how you need to proceed in case of graphical method. Now here also, so I am going down. Anyone wants to take screenshot can please take it. I am going down for analytical method. Okay. Okay. Yeah. So here, if you go for analytical method in this several masses, then here our equation would be like this: sigma mr plus MC1 RC1 plus MC2 RC2 equals to 0, right? So, and similarly for that moment also, right? So for moment we will have sigma mrl plus MC2 MC2 RC2 LC2 equals to 0. Here we are not considering MC1 RC1 LC1. Why? Because we are considering that plane C1 as reference plane. So moment generated due to force in the same plane will be 0, because there will not be any distance from that plane for the force acting in the same plane. So here you will have sigma mrl plus MC2 RC2 LC2. And once you have this, then again you can go for that sigma mrl cos theta plus MC RC LC cos theta C equals to 0. Similarly, sigma mrl sin theta plus MC RC LC sin theta C equals to 0. So from this again you can calculate that MC RC LC. By taking this on the other side and squaring and adding, you will get this MC RC LC equal to this sigma mrl cos theta square plus sigma mrl sin theta square, right? So this is how you will get this MC RC LC, and for theta, this tan theta C equal to minus the sigma MRL sine theta upon minus sigma MRL cos theta. So this is how you will get this theta c, right? Here actually theta c2, if we be more specific, here also you are getting this mc2, rc2 and lc2, right? Because here we have written that mc2, rc2, lc2. So this is how you will get this values, right, for plane c2. And when you here it was a couple balance, right, because we are considering the product of force and the distance L. So again, when you take that force balance, the sigma mr plus, as we have written, that mc1 rc1 and mc2 rc2 equals to 0. In this one again you can solve similarly by sigma mr cos theta plus mc2 rc2 cos theta c2 plus mc1 rc1 cos theta c1 is equal to 0, and sigma mr sin theta plus mc2 rc2 sin theta c2 plus mc1 rc1 sin theta c1. Here again you can make this a subject, and then squaring and adding will give you the value of mc1 rc1 will be equal to this sigma mr cos theta plus mc1 rc1 cos theta c1, this whole square, right, plus sigma mr sin theta plus mc2 rc2 cos theta c2, similarly mc2 rc2 sin theta c2, right? Again here this is whole square. So this is how you will get this mc1 rc1. And again for tan theta c1 you will have this minus sigma mr sin theta plus this mc2 rc2 sin theta c2 divided by this minus sigma mr cos theta c plus mc2 rc2 cos theta c2. So this way analytically you can calculate this required values of this mc1 rc1 and theta c1 for the balancing mass and its position in the plane c1. So once you have this idea, what you can do is you can go and calculate one problem for this also. So are you done with this particular thing? Please, you can note down these equations and also that it will be helpful to you in solving the problem. So have you noted down this?
So there is sigma mr sin theta no, in place of theta c. Last equation.
Here it is theta. Here it is theta, right? And in that here it is mc2 rc2 theta c2. Is it okay?
Yes, sir. Cos theta c also there is theta.
Okay, like this. So are you done? Then we can go for one more problem solving. Done?
Done, sir. Done, sir.
Okay. So now you can read this problem. So what this problem says is you are having a rotating shaft which carries three unbalanced masses of 4 kg, 3 kg and 2.5 kg at radial distance of 75 mm, 85 mm, 50 mm at the angular position of 45 degree, 135 degree and 240 degree respectively. Right, so here they have provided all this data of this m1, m2, m3, then radius r1, r2, r3 and then theta 1, theta 2, theta 3, all this data they have provided. Now the second and the third masses are in the planes at 200 mm and 375 mm from the plane of the first mass. So what they have given is, from this first plane they have provided this distance and this distance, right? They have provided this distance. Now the angular positions are measured for counterclockwise from the reference line log x, viewing the shaft from the first mass end. Okay, then the shaft length is 800 mm between the bearings, and the distance between the plane of the first mass and the bearings at the end is 225 mm. Now determine the amount of the counter masses in planes at 75 mm from the bearings for the complete balance of the shaft. Now the first counter mass is to be in a plane between the first mass and the bearing, and the second mass in a plane between the third mass and the bearing at that end. Right. The first counter mass is to be in a plane between the first mass and the bearing, and the second mass in a plane between the third mass and the bearing at the end, right? So the your balancing, as it is mentioned here, right, these are bearings, you can see. So the same situation, the same thing is mentioned in this problem also. So you need to find this balancing, right, masses in plane, that C1 and C2. So can you try this problem? Hello.
Okay, sir. Okay, sir. Okay, sir. Okay, sir.
Right here, actually, see, at the distance between this bearing is provided to you, so I am giving you a little bit of hint if it is required, right? So the distance between this bearing is provided as 800 mm, and the distance from this plane to the plane in which balancing mass is there is mentioned as 75 mm on both the side, here as well as here also, right? So now you can calculate this LC2, because you are provided this 75 mm, this 75 mm, this is 800 mm. Are you getting what I am trying to say?
Yes, sir.
Right? So you can calculate this now, I guess. And distance of this first plane from the bearing, this bearing, right? So from this it is given as 225. So it will help you in finding L1. Are you getting?
Sir, but in graphical method, if we mess with the direction, then the problem would be a bit complicated. But in analytical method, calculating such problems would be a bit easy, but meantime it's time consuming.
Yeah.
So for graphical method, what approach should we do for making it in a correct way?
For graphical, what problem you are telling? For graphical method?
Like
Hmm.
while drawing the vector diagram, sometimes I'm facing with problem on the direction. Which one would be the proper direction?
See, that is given here clearly, right? Angle, this theta 1, theta 2 and theta 3. So that you have to measure with your instrument, and according to that you have to draw whatever magnitude of the vector along this direction, one by one, right? So you need to be careful while you are drawing this particular diagram. Angle must be correct, right? If angle
Yes, sir.
is not
So
correct, then you will not get the right answer.
proper answer, yeah.
Yeah, yeah. So now, can you try? What you have to do
Yeah,
is,
definitely.
yeah, you have to first go with that couple balance and then force balance in order to find the balancing mass in the different planes. So are you calculating? So should I give you some of the data? Right, as LC2 I have told you will be 800 minus 2 into 75, that will be 650 mm. L1 as I have mentioned, it will be 225 minus 75, that will be 150 mm. L2 will be, it is given for 2 and 3 are at 200 and 375 respectively, right? So it will be 150 plus 200. So this will be like this, 150 plus 375, 525 mm. So once you have all this data with you, what you can do is you can calculate that M1 R1 L1 M2 R2 L2 M3 R3 L3, right? So once you calculate this, and then if you apply that sigma MRL plus MC2 RC2 LC2 equals to 0, then what you are going to get is, by considering both sigma MRL cos theta and sigma MRL sin theta, similarly MC2 RC2 LC2 cos theta 2 and MC2 RC2 LC2 sin theta 2. So if you write both this equation and then make that MC2 RC2 LC2 a subject by squaring and adding both the equation, then what you will get is MC2 RC2 LC2 will be equal to 74568, something like that, right? So once you get this, what they have provided is, they have provided RC2 as 40 in problem statement, and LC2 you have calculated as 650. So as you have this RC2 and LC2 with you, you can calculate MC2, and that will be 2.868 kg, something like that. So are you getting anything like this? Hello?
Yes, sir. Yes, sir. Yes, sir.
Right? So once you are done with this, then what you should do is you have to calculate the product of M1 R1 M2 R2 M3 R3 M2 R2 and M3 R3, and then MC RC are also with you now. So once you this MC2 RC2, sorry, right? So once you have this, then you can apply that sigma MR plus MC2 RC2 plus MC1 RC1 is equal to 0. So here also when you apply that cos theta and sin theta, and then again you can make MC1 RC1 cos theta 1 and MC2 R2 sin theta 1 as subject, and then squaring
Sir, I want to ask a question, sir.
sorry.
Sir, I want to ask a question, sir. In like a force equation that we are using cos theta 1 for a mass, then for that mass in moment equation it will be sin theta 1 in place of cos theta 1, as the angle is increasing by 90 degree.
Sorry, can you repeat your question?
मतलब सर मतलब कि एक मास m1 है, वो एक लाइन है, उससे थीटा 1 एंगल बना रहा है, तो उसका फोर्स इक्वेशन में लिखते वक्त m1 r1 cos थीटा 1 लिखते हैं x डायरेक्शन में. उसी तरीके से मोमेंट का लिखते वक्त मोमेंट की भी दो इक्वेशन बनेंगी सर. तो x डायरेक्शन में उसका लिखते वक्त cos थीटा 1, x डायरेक्शन से भी वो मोमेंट लिखते वक्त उसका जो मोमेंट का जो वेक्टर है वो थीटा 1 एंगल ही बनाएगा या थीटा 1 प्लस π/2 बनाएगा?
Mostly it will also make the same angle if you check here, because in the fourth polygon and the couple polygon it is at the same direction, if you can see here. Can you see this?
Yes sir, yes sir.
Right?
पर सर 90 डिग्री एक्स्ट्रा बनाना चाहिए ना वो थोड़ा, मैं ये सोच रहा था. नहीं,
I don't think so.
Okay sir, okay sir,
Okay. So yes, let us see here. if you follow the same procedure here also, what you will get is MC1 RC1 will be equal to 235.63, and here also you are provided that RC1, so you will be able to calculate that MC1 as 3.14 kg. So you have calculated MC1 and MC2. Similarly, that tan theta C2 and tan theta C1 also you can calculate, right, from those equation which you have calculated for that sigma MRL sin theta C2 and sigma MRL cos theta C2 and sigma MR sin theta C1 and sigma MR sin cos theta C1. Are you getting what I am trying to say? Hello.
Yes, sir.
So have you calculated theta C2 and theta C1?
So rule theta would be like 272 or like.
Actually, theta C2 is coming 329.3. It is coming in the fourth quadrant, because sine and cos both are negative, and both are negative in that quadrant only, right? Sorry, that sine is negative and cos is coming positive, so it will be in that fourth quadrant only, because you are having this all STC, right? All STC. So here for theta C2, it is coming like sine is negative and cos is positive component. So this theta C2 is lying in the fourth quadrant. Similarly, theta C1 is lying in third quadrant, because both of them are coming negative, right? This will be 253.2. Again, I think it is confusing, so it is 253.2. Okay. Hello.
Yes, sir.
So this way you will be able to solve this problem, right? Now, after having this particular problem, next is this balancing of reciprocating masses. So till now we have seen that balancing of rotating masses. Now whenever you are having that reciprocating masses, we have already calculated this acceleration of piston, right? Acceleration of piston as r omega square cos theta plus cos 2 theta by n. So in this, if you see, whenever your piston is moving, it will going to apply this force m into a, right? So mr omega square cos theta plus cos 2 theta by n will be the force. So from that, this mr omega square cos theta is known as primary accelerating force, and this mr omega square cos 2 theta by n is known as secondary accelerating force, right? So here, if you see that your particular this unbalanced force, this mr omega square cos theta is acting here, so what you can do is you can provide this balanced force like mr omega square, right? On the crank pin you can add that force. So when you are going to add that m over crank pin in order to balance this mr omega square cos theta of primary force, you can balance it with this component mr omega square cos theta. But in doing so, what will happen is it will have one more vertical component, that is mr omega square sin theta, and it is not going to be balanced. So because of this, then you will have vertical, what we can say, up and down motion of your this particular point, right? So that is why reciprocating masses cannot be fully balanced. Only a portion of reciprocating masses, the C is a fraction, right? So only a fraction of reciprocating masses are being balanced, right? And not full reciprocating masses are balanced. So Here also you can see this whatever F21V and this F41 is there, it is going to generate a couple because they are at a distance. So this couple is shaking couple, and this force which they are providing here in horizontal direction, this is known as shaking force because this force is not balanced and this particular couple is not balanced. So this is how you are having this shaking force and shaking couple present in this reciprocating masses. So what you are doing in this reciprocating masses is you are going to balance a particular portion of your this reciprocating masses. Like suppose if you see that instead of full reciprocating mass m, what you are going to do is only a portion of this reciprocating mass you are going to balance. So you will have your new component as c mr omega square cos theta and c mr omega square sin theta. So if you see in the mechanism, right, so here what will happen if you have only that fraction of this particular force balanced, then for horizontal direction it will be mr omega square cos theta minus c mr omega square cos theta, right. So it will be basically 1 minus c mr omega square cos theta. Similarly for vertical, you will have c mr omega square sin theta. So when you take resultant of this particular force, right, then it will be this r is equal to under root of sigma fs square plus sigma fv square. So total resultant force in this reciprocating masses will then be 1 minus c mr omega square cos theta whole square plus c mr omega square sin theta whole square. So this is how you will have your resultant in case of reciprocating masses. So this is the what we can say particular case of reciprocating masses. So basically, if you are having revolving unbalanced mass also, right, then you have to add it to this whatever cm we have balanced here, right. This in place of m, what we have done is we have only provided cm. But if you are having revolving part also, then you have to add that revolving mass also, right. That we will see when we will solve this problem, I guess, above given problem. Let us see that problem. Here what is given is the following data relate to single cylinder reciprocating engine. Mass of reciprocating part is 40, mass of revolving part is 30 kg at crank radius. Now speed is 150 rpm, stroke is 350 mm. If 60% of the reciprocating parts and all the revolving parts are to be balanced, so see, this is important thing, 60% of the reciprocating parts and all the revolving parts are to be balanced, then you have to determine the balance mass required at a radius of 320 mm. So radius of that balancing mass is provided. Now on an unbalanced force, when the crank is turned 45 degree from the top dead center. So unbalanced force also we have seen what is the unbalanced force, right? The last whatever we have calculated, the resultant unbalanced force in the reciprocating part is that 1 minus c mr omega square cos theta square and the c mr omega square sin theta square. That is what we have
सर
mentioned.
may please tell that where this c came from? ये fraction कैसे हुआ?
See, this fraction has come into picture because you cannot avoid this vertical component mr omega square sin theta when you are balancing the reciprocating component of this mr omega square cos theta. That is why instead of going for full balance, you are going for partial balance. So generally this value of c is varying from 1 by 2 to 3 by 4, right, and not the full reciprocating mass you are balancing, because otherwise this component is going to give that vertical motion to this particular fulcrum. Right?
Sir, if a counter mass reciprocates in the vertical direction against the uh, already balanced mass, so will it be fully balanced, like in a hypothetical case?
Sorry, can you repeat?
Sir, I'm saying that like if a counter mass reciprocates in the vertical direction,
Counter mass reciprocates in the vertical direction. Okay. Uh.
so will it be fully balanced or not?
See, here the question is, here it is rotating in horizontal, so you are having unbalanced component in vertical direction. You are telling that it
Right.
will oscillate in vertical, then it will be in
No, no,
horizontal.
no.
What I am saying is,
Uh,
are you getting
and
it?
another another mass.
See, actually I am not getting then what basically you are trying to say. So if
सर
you
Oh,
will
सर
have
मतलब ये कहना चाह
the
रहे हैं, जैसे
oscillating,
वी बैलेंसिंग जो करते हैं ना,
yes.
90 डिग्री पर एक और रेसिप्रोकेटिंग उसको प्लेस कर देते हैं, उसके बारे में कहना चाह रहा है सर.
How will you add that actually whatever you are going to add.
नहीं सर, मैं ऐसे हाइपोथेटिकल केस बता रहा हूँ कि अगर मतलब कि
Hmm.
एक मतलब वर्टिकली कोई रेसिप्रोकेट करे, मतलब यहाँ से लेके क्या नाम है, ये जो अ, जहाँ पे मतलब क्रैंक घूम रहा है वहाँ पे मतलब वर्टिकली कोई रेसिप्रोकेट करे
Hmm. Hmm.
और मतलब उसी उसी क्या नाम है, उसी एंगुलर वेलोसिटी पे जिस पे मतलब ये पिस्टन मूव कर रहा है,
Hmm.
तो बैलेंस हो सकता है?
I
सर
guess
सर ऐसा
we
ही तो
need
वी
to
बैलेंसिंग में करते
check.
हैं सर.
In short, if you are going to provide this mr omega square sine theta hypothetically in the opposite direction, then you can balance, right? As you are telling hypothetically.
यस सर. ओके.
Okay, okay, okay.
सर वी बैलेंसिंग में भी तो ऐसा ही करते हैं जैसा ही बोल रहे हैं.
Sorry. See, wheel balancing is not a case of reciprocating balancing, right? Wheel balancing is the case of this rotating balance, and rotating masses can be fully balanced. So, wheel balancing is not the case of balancing of reciprocating masses. Are you getting me what I am trying to say?
यस सर, यस सर.
Okay, okay. So as we have seen earlier, in case of that rotating unbalance, we are achieving almost full balanced force in case of rotating unbalance. But in case of reciprocating unbalance, it is not possible. That is what the point is. Okay. Okay.
यस सर, यस सर.
Now can you try this question? Hello.
Yes, sir.
So please try and answer this question then. Be a little bit quick, huh? So see what amount of mass you need to balance is that fraction of this reciprocating masses, right? Plus full revolving masses. So reciprocating mass is given as 40 and revolving is 30 and C is provided as 0.6, right? So the total mass needs to be balanced will be 54. Is it correct? Hello.
Yes, sir.
So once you have this total mass needs to be balanced, what you have to find is that balancing mass required, right? That you need to find. So that can be simply calculated from this MCRC is equal to M into R. So this 54 kg will be your M, and crank radius will be half the stroke length, that is 175 mm, right? So in that, now what you are provided again is radius of 320 mm for balancing mass is provided. So you are having everything except the balancing mass required. Are you getting it? Hello.
Mhm. Yes, sir. Yes.
So what is MC in that case? MC into 320 is equal to 54 into 175. That will give you 29.53 kg. Right? Everyone is getting the same? Hello.
Yes, sir.
And in
So what
case
is RC?
RC is the radius of balancing mass which is provided here. Balance mass required at a radius of 320 mm. Okay.
Okay, sir.
Right. So now this is clear. And this unbalanced force now you can calculate easily from the equation we have written. That resultant unbalanced force we have calculated, right? 1 minus CMR omega square cos theta whole square plus CMR omega square sin theta whole square. Okay. Hello.
Yes, sir.
So can
Actually,
you
sir,
theta is
this topic is
45.
bit.
Theta is 45 here provided, right? Yes. Someone was telling something.
Yes, actually, I was telling that this topic is bit difficult. Actually, there's bit void knowledge on this topic, so facing bit
So
इतनी फास्ट थोड़ा
actually see we have to have what we can say something kind what we can say we cannot have that time to go uh, in depth for each particular thing, right? But I am trying to
Yes, sir. Yes, sir.
still
Yeah, yeah.
make
Definitely, sir.
you
Definitely. But yeah, we have to focus on it. So that's what I am telling.
yeah, yeah, yeah. It may be a little bit fast, but I guess I am trying to also cover whatever basics are there,
Yeah,
right?
definitely, sir. Definitely, sir. Definitely.
Yeah, yeah.
Actually, sir, we have bit void knowledge on this topic, so therefore I have to focus on it. That's what I was.
Okay, okay. So anyone has calculated this, what we can say, that unbalanced force? Please type in. This is the equation, right, which we have write for this unbalanced force. Unbalanced force present in reciprocating masses, right? So everything is with you in this case. See here M is only that reciprocating mass only, right? So you need to take care while you are calculating this. So here M is 40 only. Here you need not to consider that M as that 54. So this both are different thing. So R is provided as 0.175, C as 0.6. Then omega you have to calculate from RPM, that is 15.7. Theta is given as 45. So what are you getting for this unbalanced force? R is 0.175. This omega in both the cases 15.7. Theta is 45. So can anyone tell the answer? C is 0.6. Can anyone tell the answer?
880.7.
Sorry. 880.7. Yes, that is the correct answer. Anyone else is getting that answer?
Sir, I am getting 879.8.
879.8, that is also correct. Okay, so many of you are getting it correct. So let us move forward. So now balancing of locomotive. So here in case of locomotive, you are having different types of locomotive, inside locomotive, outside locomotive. So you are having two engines in which cranks are 90-degree apart, as here it is mentioned in your problem statement, right? So you can have that cylinder inside the what we can say wheels plane. This may be the plane of wheel, right? And if you are having inside locomotive, then your crank plane will lie inside. And in case of outside locomotive, what will happen is you will have plane of wheel, and that crank will lie outside if you are having outside locomotive. And one more thing is that if coupling rod of locomotive will be there, then plane of coupling will also be added. So basically, in case of balancing of locomotives, you will have this unbalanced mass in different plane, and again you have to balance it. So if we go for specific things in case of that locomotives, then these three are the main forces or couple you have to take care when you are talking about this locomotives. So hammer blow is nothing but the vertical component which is trying to lift the locomotive, right? It is vertical component as we have seen, and it has maximum value of that mr omega square, because its vertical component is nothing but mr omega square sine theta, and its maximum value will be mr omega square only, right? And it is going to consider only reciprocating part, right? So this is the hammer blow which is acting in vertical direction, right? So these things you need to remember, right? Because sometimes short questions may also be asked from this concepts only, right? Now once you are done with this hammer flow, next is this variation of tractive force. Now variation of this tractive force is going to come into picture because of that particular horizontal component, that is 1 minus c mr omega square cos theta. As you have seen, if we discuss about this variation of tractive effort, see here it is effort, so it is the force, right? So it is this 1 minus c mr omega square cos theta. This is horizontal component as we have seen recently, right? In case of balancing of the reciprocating masses, this is the unbalanced force in horizontal direction, 1 minus c mr omega square cos theta. Now in case of your locomotive, you will have two cylinders. So if you consider this as cylinder 1, then you are having that second cylinder also. In that, this force will be 1 minus c mr omega square cos theta plus 90 degree, because crank are 90 degree apart. So that is why this in cylinder 2 it will be 1 minus c mr omega square cos theta plus 90 degree. And if you further simplify, then it will be 1 minus c mr omega square sine theta, right? So if you see total unbalanced this primary force or total this variation of this tractive effort, then it will be 1 minus c mr omega square cos theta minus sine theta, right? That is total variation of tractive effort. Now if you see when it will be maximum, then you can directly say that all these are constant, right? 1 minus c mr omega square is constant. So it will depend on this cos theta minus sine theta. So when this cos theta minus sine theta will be maximum, at that point you can have this maximum variation of tractive effort. And if you see this, you will have this minus sine theta minus cos theta is equal to 0. So this will give you tan theta is equal to minus 1, right? So once you have this, then theta will be equal to, in case of tan theta is equal to minus 1, as you know, theta is either 135 or 315, right? So once you put the value of this theta into the equation of this total tractive effort or total variation of tractive effort, what you are going to get is, while putting theta is equal to 135 or 315, you will get final as plus or minus root 2 1 minus c mr omega square. So this can be the maximum values of total variation in tractive effort. Now one more thing was there, and that was swaying couple. So in swaying couple, actually you are having this way, I am drawing this, this may be center line, right? So you are having, suppose this as 1 minus c mr omega square cos theta, and then this can be considered as 1 minus c mr omega square cos theta plus 90. Then this both you can consider at an angle, let us say L by 2 from the center line. So if this both are at L by 2 from the center line, then here we are discussing about couple, right? So if you take moment about the center line, then you are having swaying couple as 1 minus c mr omega square cos theta L by 2 minus, because here see direction of couple is different, one is clockwise, other is anti-clockwise. So here 1 minus c mr omega square cos 90 plus theta L by 2, right? So if you further simplify, you will get 1 minus c mr omega square, L by 2 is common for both, so 1 minus c mr omega square cos theta plus sin theta. And here also 1 minus c mr omega square L by 2 is constant, this is constant. So this cos theta plus sin theta, when it will become maximum, at that point this swaying couple is going to be maximum. So you can find here minus sin theta plus cos theta is equal to 0, which will give you tan theta is equal to 1, which will give you theta may be equal to 45 or 225, right? So when you put theta is equal to 45 or 245 into this main equation of swaying couple, then maximum swaying couple will be equal to this plus or minus one by root 2 1 minus c mr omega square L. So this is how you can have that maximum swaying couple and maximum variation in tractive effort and hammer blow in case of locomotive, right? Hello.
सर थोड़ा ऊपर करना है सर.
Yes.
Sir, it will be 1 by root 2 swing.
Plus or minus 1 by root
सर
2.
ये हमें सर पीपीटी में मिल जाएगी सर ये.
हाँ, I will upload these notes after this session. In that drive
Sir,
link.
where you will upload?
In that drive link which
Drive
I have
link.
shared in the chat box.
सर ये तो क्वेश्चन
Sorry.
एक बार और सर वो कर दीजिए सर.
Yes.
जो लिंक है सर वो शेयर कर दीजिए सर दोबारा.
It will be there in the chat box only, right? This.
सर मुझे नहीं दिखा ना सर, इस वजह से कह रहा हूँ दोबारा कर दीजिए.
It is there only, right? I have again shared that link. Okay.
Sir, in that equation it was sin theta plus cos theta.
Yes.
Then theta equal to, then it will be root 2 into 1 minus c.
Sorry.
Instead of 2, sir.
Sorry.
Sir, instead of 1 by root 2, will it be root 2 or same?
If you put theta is equal to 45 here, then it will be 1 by root 2 1 minus m r omega square, right? Into L.
सर वो sin थीटा प्लस cos थीटा है ना इक्वेशन में.
Yes.
तो रूट 2 हो जाएगा ना.
Yeah, 1 second. Yes, 1 second. See, it will be this 1 by root 2 only, because 1 by root 2 plus 1 by root 2 will be 2 by root 2, right? And 2 will be cancelled with this 2. So it will remain that 1 by root 2 1 minus CMR plus 1 by root 2.
Okay, sir. Okay, sir.
Correct?
Sir, I have a question.
Okay, so it will be like this only.
Hello, sir.
Yes.
Sir, what is the effect of swing couple on engine?
See, as it is mentioned here, it will try to sway the, what we can say, that wheel, as it is mentioned, because it is the couple, right, acting on your this particular plane, right? So that is why it is going to sway that engine, right? As you can see here, it is because of the couple about the center line.
Okay, sir. And that is your tractive force, sir?
Sorry.
And tractive force, sir? What is the tractive force?
Tractive force, it is along that what we can say, along that primary force only, that it means horizontal direction. What will be the that maximum unbalanced force, because this 1 minus CMR omega square cos theta is along that horizontal direction, right, as we have seen. Similarly this also. So what will be the total that horizontal unbalanced force, or what can be the maximum total horizontal unbalanced force? That is variation of tractive effort.
That means the only horizontal force is tractive force.
Yes. Okay.
Okay, sir.
So can
Sir?
you, yes.
Sir, in the case of swaying couple, the orientation of the engine is perpendicular or vertical?
Whatever we are discussing is, I guess, horizontal only.
In the line with the tracks?
Yes.
Okay, sir.
Okay. So
Sir,
here
in the
this example is,
sir,
yes.
sir, in swaying couple, will the tractive force be zero?
In
Uh,
in swaying couple, tractive force is zero. It means, what do you mean?
I mean, if there are two engines, then are they cancelling the vertical component?
I Actually they are in different planes, na, I guess.
Okay,
Here
sir.
there are different plane for cylinders, right, as I have mentioned here, right? Are you getting?
Yes, sir.
Okay. So can you try this particular question with this following data? Right here, 2-cylinder uncoupled locomotive is there. So rotating mass per cylinder is given, reciprocating mass per cylinder is given, then distance between wheels, and then distance between cylinder centers, then this threads of diameter of this driving wheel is given, then crank radius is given, then radius of center of balance mass is given, then locomotive speed is given, angle between cylinder and crank is given, and dead load at each wheel is given. Right, and then what you have to determine is balancing mass required in the plane of driving wheels if whole of the revolving and 2/3 of the reciprocating mass are to be balanced. That you have recently done, right? Hello.
Yes, sir.
Okay, then this
Yes, sir.
swaying couple you need to do, then this variation in the tractive force you need to do, then maximum and minimum pressure on the rails, and then this speed of locomotive without lifting the wheels from the rails. So we can see all one by one. So if you go for the first one, right, then it is very simple. Total mass to be balanced will be that fraction of reciprocating mass plus full of revolving mass. So fraction is given as 2/3, reciprocating mass is given as 300, and revolving is given as 280. So you will have 480 kg of mass needs to be balanced. Yes or no? Correct? Hello.
Yes, sir.
So now here what you have to do is you have to consider this 4 different plane, right? And you have to take one of the plane as what we can say reference plane, right? If you consider this 1, 2, 3 and 4, right, then it is inside cylinder maybe, so C1 C2 may be here, this may be your will, right, 1 and 2. So if you consider this plane 1, 2, 3, 4, then what you have to do is you have to take 1 as reference plane, right, and consider that theta 2 is equal to 0 degree, right, and then you can start with the equilibrium of that forces and all, and then you can calculate first the balancing mass required in plane 4, right, and then balancing mass required in plane 1, right. So you will find something m4 cos theta 4 and m4 sin theta 4 equals to something. Once you find this, then you can calculate first m4 and then tan theta 4. Similarly, once you calculate that, then you can again come and calculate this m1 as we have done previously. So this thing we are not repeating here, but what we are going to do is we are going to calculate the swaying couple. So can you calculate swaying couple? Just now we have seen the equation, right? Plus or minus 1 by root 2 1 minus c mr omega square into L, right? This is the maximum swaying couple. So you are provided that c is 2 by 3, m is 300, r is 0.3, that omega, if you calculate from that rpm, or then it will be 15.43, that is the omega, right? Omega you need to calculate from actually this v, this is locomotive speed, and radius is provided. This diameter can be converted to the radius. So omega you have to calculate from this v by r. You have to convert this 50 kilometers per hour into meters per second, and then this 1800 mm of diameter to radius, that is 900 mm. So from that you will find omega as 15.43 radian per second. So and L is given as 0.6, right? So distance between cylinder centers, that is the L, as we have seen while calculating the swaying couple. So are you getting what I am trying to say? Anyone can respond? Hello? Hello?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Right, so this way you can calculate this swaying couple, right? Similarly, variation in tractive effort also we have seen that plus or minus root 2 1 minus c mr omega square. Here also you are having all the values with you, so this also you can calculate, right?
So swaying couple is 196.
Swaying couple is coming actually 30.3 Newton meter, 3030.3 Newton meter. This is coming 3030.3 Newton meter, and this is coming as 10,100 Newton, right? So now in case of this two question, we can elaborate on this. See here, maximum and minimum pressure on the ray will be able to be calculated with hammer blow. So in hammer blow you are having that m r omega square, but this m is only whatever that balancing mass is required for reciprocating part. So if you have calculated this m1, right, or m4, that both are coming as 178.7. So it will be a fraction of that particular whatever balancing mass required. This m will be fraction, see, 178.7 is the balancing mass which is coming. Now what is the fraction of reciprocating mass you are balancing? That is 2/3 of this 300, and over there also total is 480. So from this normalization you will be able to get that in balancing mass whatever amount or fraction is balancing the this reciprocating mass. So once you get that m, then you will be able to calculate the hammer blow. Right, radius of center of balance mass is given as 620 mm, right? So hammer blow will consider that radius 0.62 meter, and mass is this mass, and omega you have already calculated. So if you put all this value, then your hammer blow will come around 10,991 Newton. Right. So once you are done with this, then what you have to do is you have to simply add this dead load, which is given here. Dead load, this 3.5 ton. So I'm going here, right? If you have that dead load of 3.5 ton, that is 3.5 into 1000 into 9.81, that is the 3.5 ton, right? So it is almost around 34,335 Newton. So it is acting downward because it is the dead load. So whatever hammer blow component you have calculated may act upward as well as downward, right? So that particular 10,991, that is the hammer blow, which can act in both the direction, upward as well as downward. So when it is upward, it will be added to this, and when it is downward, when it is downward, it will be added to this, and when it is upward, it will be subtracted from this. So which will give you maximum and minimum pressure. Right, so this is how you can calculate maximum and minimum pressure. So one more thing they have asked is at which particular point or at which speed your this particular will start lifted. So that will be when exactly this hammer blow will be equal to 34,335, which is equal to the weight of this particular locomotive. So when this 34,335 Newton will be equal to that mr omega square, that m which we have calculated the normalized is 74.46, r is 0.62 given, and omega square you have to calculate, or rather omega. So omega will be 27.27 radian per second. So if we go beyond this speed 27.27, then this hammer blow component will try to lift the locomotive. So that is what the important thing is. So this is how we are having this omega, and once you have omega, they will also ask the velocity of the wheel. So velocity of the wheels will be given as omega into r, right? So this omega you have already calculated 27.27, and r is what, that 1800 mm by 2, right? This is meter per second. You can convert it into kilometers per hour by multiplying it to this 3600 upon 1000. So if you do so, then the final answer may be around 88.36 kilometers per hour. right? So like this you can calculate this one. So is it okay? Hello.
Okay, sir.
Yes, sir. Yes, sir.
Okay. So now we will go to the next one, that is secondary balancing. So till now what we have seen is this primary balancing, right? That MR omega square cos theta we were balancing. Now secondary force is that MR omega square cos 2 theta by n. So in order to what we can say balance that, what you are assuming is you are taking that actual and imaginary crank. So what will happen is, here the angular velocity omega of actual crank, angular velocity for actual will be omega, and for imaginary it will be 2 omega. Similarly, length of crank will be r for actual, and for this secondary or imaginary it will be r by 4n, and mass will be same, right? Mass will be same for both the case. So this mr omega square cos 2 theta can then be written as this mr into 2 omega square by 4n into cos 2 theta, like that. So here one more thing is important to note, that when this particular crank, primary crank will move by theta, secondary crank will move by 2 theta. So these are some of the assumptions in order to go for this secondary balancing, right? So basically secondary balancing is that mr omega square by n into cos 2 theta that we have seen in the very first page, right? I guess for this reciprocating mass, when we have started, we have seen this, that it is having the mr omega square cos theta plus cos 2 theta by n. You can see here. Can you see this? Hello.
Yes, sir.
Okay, so this is how we are having this secondary balancing. Now next is this balancing of inline engines. So basically when you go for this inline engines, as we have seen, that you need to balance all the required things like primary force and primary couple, similarly secondary force and secondary couple. So you need to balance all these things in order to have complete balancing. So here you can have force, as we have seen, that sigma mr omega square cos theta, and couple will be sigma mr omega square L cos theta, right? Similarly here for secondary force, if you write for secondary force, then it will be mr in place of omega 2 omega, right? And here in place of r by 4n is there, and in place of theta 2 theta is there. For couple, simply L will be multiplied 2 omega square by 4n, here L cos 2 theta. So this way you have to consider for inline engines that all this primary force polygon, primary couple polygon, secondary force polygon, secondary polygon must be closed, right? Then only you can say that these are balanced, right? So once you are done with this, then if you take particular case of this inline engine, then I have taken this inline 2-cylinder engine, and in that I have shown here that in inline 2-cylinder engine you are having this crank at 180 degree apart, theta and theta plus 180. So if you consider primary force and couple polygon, right? So here it is primary force and couple polygon, here it is secondary force and couple polygon. So if you see here primary crank, here secondary crank, right? Secondary crank are at angle 2 theta, right, as you can see, and primary cranks are at angle theta. So if you see for that force, you can see here for primary force, if I write for inline two cylinder engine, then it is mr omega square cos theta, right, for this crank 1. For crank 2, it is mr omega square cos theta plus 90. So cos theta plus 90, sorry, 180 is given, right, sorry, cos theta plus 180. So when you write that cos theta plus 180, here cos theta plus 180 is minus cos theta. So primary force will be 0, as you can see here, mr omega square cos theta, and here this mr omega square cos theta minus, because here it is having change of sign in case of cos when theta plus 180 is there. So this primary force will be 0. For primary couple, it will be mr omega square L by 2 cos theta, right, and again here actually minus of mr omega square L by 2 cos theta plus 180. Why here minus? Because in case of couple you are taking reference plane here, so both the couple are having different directions, so that is why one is subtracted from the other, and because of that you will have primary couple as this mr omega square, right, L by 2 plus L by 2 will be there, because here cos theta plus 180 will be minus cos theta. So if I take cos theta out, then L by 2 minus plus L by 2 will be there. So mr omega square into L into cos theta will be there for primary couple. Now for secondary force, it is mr omega square cos 2 theta by n, if I simply write. Then for here it is again mr omega square cos 360 plus 2 theta by n. So it will be added because both will be in the same direction, as you can see. But for couple again, what will happen, as it is in the same direction, for couple it will be subtracted. So for secondary couple you will get 0 in case of this inline two cylinder engine. So in inline two cylinder engines with cranks are 180-degree apart, primary force and secondary couple are balanced, because primary force is coming 0 and secondary couple is coming 0. So what you need to take care is this primary couple and secondary force. This way 4-cylinder and 6-cylinder engines are also discussed in Ratan. You can explore that. I am not going into deep of it, because we need to solve some questions also. So we will go quickly, right? So is it okay for you, because we need to solve some questions also? You will be able to solve that or what? Hello? Hello? Can you hear me?
Yes, sir. Yeah.
Right, so here balancing of V engines and balancing of radial engine is also there, but I will go quickly for this because you need to solve some questions after this. So here in case of this balancing of V engine, please mute yourself, somebody is unmuted. Hello? Yeah. So in balancing of this V engine, you can have this crank OA and this which is attached to the slider B1 and B2 through this AB1 and AB2. So in this case, if you take primary force for cylinder 1 along OB1, then it will be mr omega square cos theta minus alpha, right, along OB1. Similarly, if you take component of that mr omega square cos theta minus alpha, here because it is theta minus alpha, right, they are talking about this angle, it is theta minus alpha. So when you consider this component along OB1 in the x direction, then it will be mr omega square cos theta minus alpha cos alpha, right, it is along x. along x direction. Right. Now for primary force into that second cylinder, that is mr omega square cos theta plus alpha, right, along OB2. So here this angle they are talking about, this is theta plus alpha, and if you take a component of that particular along OB1 in the direction of x, then it will be mr omega square cos theta plus alpha cos alpha along x. So once you done with this, then total component along x direction you can calculate by adding this 2 and simplifying it. You will get 2 mr omega square cos square alpha cos theta. Similarly, if you take along z-axis, right, you will find it that component will be 2 mr omega square sin square alpha sin theta. Right, from this two component you can calculate resultant, and you can also calculate that tan beta from this two component, like sin square alpha sin theta upon cos square alpha cos theta, like this. Right, so this is all we have considered is primary force. The same you can also do with secondary force. In that, mr omega square by n cos 2 theta minus alpha and cos 2 theta plus alpha will be there. Again you will take components along x-axis and z-axis, and again you will find that resultant, as well as again you will find the tan beta dash. Right, so I am not mentioning all these things again here for this V engine. Right, so you can do that in short. Right, so this is how you can have balancing of V engine. And finally this balancing of radial engine. In balancing of radial engine, what they are doing is they are actually using a method of direct and reverse crank in case of this radial engine. They have considered the direct and reverse crank. Suppose OA is direct crank, OA dash is reverse crank. It is moving in, OA is moving in anti-clockwise direction, OA dash is moving in clockwise direction. So this is how at all point of time you will have this mr omega square cos theta as your component along this horizontal direction, and vertical direction component will be nullified because they both are moving in opposite direction to each other. Same is true for the secondary crank also. Here primary direct crank, secondary direct crank, primary reverse crank, secondary reverse crank. So this way you can have that balancing of this radial engine, in which you will use this direct and reverse crank method. Right, so now let us quickly go through the questions. So K 2005. So here if you see the question, a rotating disc of 1 meter diameter has two eccentric masses of 0.5 kg, each at radius 50 mm and 60 mm at angular positions of 0 degree and 150 degree respectively. A balancing mass of 0.1 kg is to be used to balance the rotor. Now what is the radial position of the balancing mass? So what they have asked is RC, right? In MCRC they have asked RC. MC is provided as 0.1 kg. What you have to do is that sigma mr plus MCRC is equal to 0, sigma mr cos theta plus MCRC cos theta equal to 0, sigma mr sin theta plus MCRC sin theta equals to 0. From this you will get it. Can you quickly try this? Hello? Hello? Hello?
Yes.
Hello?
Yes.
So 0.5 into 50 M2R2, 0.5 into 60. So 50 into 0.5 will be 25, 60 into 0.5 will be 30. So 25 cos 0 plus 30 cos 150 plus MCRC cos theta c equals to 0, and then here it is 25 sine 0 will be 0 anyway, right? So it will be 0 plus 30 sine 150 plus MCRC sine theta c equals to 0. So once you write this, then you can square and add both, right, in order to get MCRC. What you have to do is this 25 plus 30 cos 150 square plus 30 sine 150 square. So RC is given, you find MC. Sorry, MC is given, you need to find RC. Can you tell me quickly? Hello? Hello? Ashar Zaman has raised hand. Hello?
No, sir, it was by mistake.
Okay, okay. So anyone is done with the calculation? Hello?
Yes, no.
See, I have given you this final equation in order to calculate that RC, right? This one. In this MC is 0.1 they have provided. So can you tell me?
Okay.
You just need to give simplification. Please be quick.
Yes, sir. Yes, sir.
Sir, sir, RC is equals to 150 mm.
Yes, correct. So here RC will be equal to 150 mm. Okay. Then if you go for the next one, then what is mentioned here is a slider crank mechanism is slider mass of 10 kg, stroke of 0.2 m, and rotates with a uniform angular velocity of 10 radian per second. The primary inertia force of the slider are partially balanced by the revolving mass of 6 kg at the crank, placed at a distance equal to crank radius. Okay, then neglect the mass of connecting rod and crank. When the crank angle is 30 degrees, the unbalanced force normal to the slider axis is. So what they have asked, can you tell me and try this? First, what they have asked, can anyone tell? What is this unbalanced
Yes, sir.
force in
Yes.
normal to the slider axis? Can anyone tell this?
Sir, is that meaning that the unbalanced force
Normal to
we
the slider axis, it means vertical
is
direction.
vertical direction?
So what we have seen in vertical direction, what is the force? MR omega square sine theta. Yes or no?
Yes, sir. Yes, sir.
So now we can calculate it, right? Then calculate it.
Okay, sir.
Yes.
Sir, will it be like 30 Newton or like?
Yes, correct. Exactly. So any of you are getting the same? Hello?
It's 30 Newton, sir.
30 Newton, correct. but that should also response.
Yes, sir, 30 Newton.
Everyone is getting 30 Newton, right? What mass you have considered?
So 6 kg.
Mass is 6, right? As it is mentioned.
Yes, sir.
Mass is 6, radius is
0.1.
0.1 meter.
0.1 meter because stroke length is 0.2.
Yeah.
Omega is 10 provided.
10 radian per second. And
Right.
theta is 30 degree.
Theta is
Yeah.
30. So when you put all this, your answer will come around 30 Newton, right?
Mhm.
Okay. Then next is this one. So here, if you see, two masses M are attached to opposite sides of a rigid rotating shaft in the vertical plane. Another pair of equal mass M1 is attached to the opposite sides of the shaft in the vertical plane as shown in the figure. Consider M is equal to 1 kg, E is equal to 50 mm, E1 is equal to 20 mm, E is equal to 0.3 mm, E is equal to 2 meter, and A1 is equal to 2.5 meter. So for the system to be dynamically balanced, M1 should be how much? So the simple moment balance, I guess you can try. If you consider what we can say, this plane as reference plane and take moment of all the forces, then if you start with this M1, it will have this direction, right? Here also it will have this direction. So this both will be added and this can be subtracted because it is having different direction than the remaining two. So if sigma of moment about reference plane, if you are taking 0, then your M1 into that distance is provided as 2.5, right? A1, right? So actually this is L. Let me write L at the end. Before that, radius is important, right? So what is E1? 20 mm. 20 mm means 0.02, right? So MRL only I am writing. Omega square I am not writing because it is same for all are on the same rotating element. So MRL is there. 1 second. Similarly, this M and E is given as 50, so it is 0.05, and the distance of that will be 0.3 because B is given as 0.3, and minus this 1 kg. 1 kg is at again 0.05, 50 mm, and distance for that is 2.3 from the reference plane will be equal to 0. So in this you are provided this value of M, that is 1 kg, right? So here M is 1 kg. So the only unknown is M1. So you can quickly calculate M1 from this. Yes or no?
Yes.
So what is M1?
M1 is 2 kg, sir.
Yes. So M1 will be 2 kg. So let's go quickly to the next one. So here the three masses are connected and rotating shaft supported on bearings A and B as shown in the figure. The system is in a space where gravitational effect is absent. Now neglect the mass of shaft and loads, and M1, M2, M3 are given, right? And angular speed is given. Magnitude of bearing reaction at location B is. So you need to find this bearing reaction at B. Right here, M1, M2, M3 are on the same plane, right? As you can see here. So can you try this question?
Yes, sir.
So what you have to do is you have to calculate sigma fx and sigma fy for this. in order to calculate the bearing reaction RB.
Okay, sir. Got it, sir. Got it.
So mr omega square cos theta, you can neglect omega square here actually. You can directly go for sigma mr cos theta, sigma mr sin theta.
Sir, why should we neglect the omega square? For what
because
reason?
because omega is same for all the, what we can say,
Okay.
component, and when you go for this it will not affect. Hmm.
Sir,
In
will it be
case,
the zero for both cases?
yes, it is coming 0 for both the case. When you go for that sigma mr omega square cos theta and sigma mr omega square sin theta, it is coming 0. So RB will be also 0, because RB is nothing but the under root of this sigma fx
Oh yes, sir.
and sigma fy.
Plus,
Right?
yeah.
So this way you will find it 0 only. So next is two masses A and B having mass ME and MB respectively lying in the plane of figure. Now they are rigidly attached to a shaft which revolves at about an axis through O, right, perpendicular to the plane of the figure. Now the rate of rotation of masses MA and MB are RA and RB respectively. The angle between OA and OB is 90 degree. MA is given 10 kg, MB is given 20 kg, RA and RB are also provided. Then the balance mass to be placed at a radius of 200 mm is. It is very straightforward problem, right?
So didn't get it. I mean,
See, these are very simple questions in comparison to what we have
so
seen.
then similarly omega will be cancel out as
Here also
will,
it will be cancelled out, yes.
okay.
See here, if you think of force polygon, then that A will be in this direction, right? At point A, it will be in this direction. At point B, it will be in this direction. So the resulting will be like this, right? So here, as you are having this 90 degree of angle, your MBRB can be directly calculated from this M1R1 square, sorry, M1R1 M1R1 square plus M2R2 square, because it is having only one vertical component and one horizontal component, right? It is straightforward, right?
Yes, sir. Yes, sir. Now got it, sir. Yes.
So quickly calculate it.
Sir, approximately 41.2312.
41.23, correct. It will be 41.23 because MB into RB is given as
Yes, sir.
200.
40 square, root of 40 square plus
M1
root of 10 square. Yes.
10 into 200 plus 20 into 400 square. So it will give you 41.23. Correct? Okay. Now next is this one. Here also a simple question. A balanced rigid disc mounted on a rigid rotor has four identical point masses, each of 10 grams, attached to 4 points on the 100 mm radius circle shown in the figure. The rotor is driven by a motor at a uniform angular speed of 10 radian per second. If one of the mass gets detached, then the magnitude of the resultant unbalanced force on the rotor. What they are asking is, if one of the mass gets detached, then the magnitude of resultant unbalanced force. So if one of them is going to be detached, then also, see, there are four masses, right? So if one of them is going to get detached, then this will be the unbalanced, because other two will still balance each other, right? Are you getting me?
Sir, please repeat it once again, because
See,
one if
if one is going to get detached, then
detached, then
other two will
rest,
still
yeah,
balance each other.
balance.
This one will be
Yes.
going to be unbalanced. Are you getting me?
Yes, sir. Yes, sir.
Right? So you need to calculate for this one mass, which is of 10 gram. Its radius is also given, right? 100 mm radius circle. So 10 gram is 10 by 1000 kilogram. Radius is given as 0.1 meter, and omega is 10 radian per second, mr omega square. This will be your answer.
Point one.
Point 1, right?
0.11, yeah.
Yes, so point 1 is the answer. Point 1 Newton is your answer. Now next is this we have seen, right? Consider a reciprocating engine with length radius r connecting road length L, then the secondary unbalanced force in this case has equivalent to primary unbalanced force due to a virtual crank. We have seen that imaginary crank, right? For secondary unbalanced force, we have seen that imaginary crank, right? So what is the radius of that imaginary crank?
Sir, will it be d radius L by 2 rotating at twice the engine speed?
Sorry,
D.
are you sure?
Sir, it seems like.
That is B, sir.
See,
B, Bombay.
no, actually we have seen that, right? The radius is r square by 4l and rotating as twice the engine speed, right?
Okay, sir. Yeah.
So,
Yes, sir. I see. R square by 4. Yeah.
right, we have mentioned all this,
At
right?
twice the engine.
So it is r square by 4l and rotating it
Sir,
twice.
sir, as it's will R square like the one like the hypotenuse as it is getting as we getting the radius R square by 4l as it's calculated by the hypotenuse of the crank or like that, as it is imagined as an hypotenuse of the crank or like that.
See, actually it is very simple. What we have seen is r by 4n. If you remember, we have seen r by 4n, right?
Huh.
Imaginary crank length r by 4n, where n is nothing but obliquity ratio l by r.
L by R, yes, sir.
So if you put this simply, you will get this r square by 4l. Are you getting me? Right? It is simple.
Yes, sir. Now got it.
Okay. So the last one is this one. A rigid body in the xy plane consists of 2 point masses 1 kg each attached to the ends of the two massless rods, each of 1 centimeter length, as shown in the figure. Now it rotates at 30 rpm counterclockwise about the z-axis, passing through point O. Now a point mass of root 2 kg attached to one end of a third massless rod is used for balancing the body by attaching the free end of the rod to point O. Now the length of the third rod is. So what you are asked is the balancing
Resultant
radius.
force, sir.
Balancing radius you are asking. The length of the third rod. That is balancing
No,
radius.
we have to calculate the resultant force. We could get easily of that, like the vector, like
That
we
is also
did
that
in
is
the
also
vector.
that is also fine. So once you get MCRC, then MC is given root 2 kg, right? So then you need to calculate RC. So here also angle between these forces is 90 degree to each other.
90 degree.
So again you can simply go by that MCRC is equal to this under root of M1 R1 whole square plus M2 R2 whole square. Yes or no?
Yes, sir. Yes, sir.
So if you calculate this, tell me what you are getting.
1, sir. One.
Here it is 1, here also it is 1, right? And here MC is root 2.
Root 2.
RC.
Root 2. Right.
So
Hmm.
RC will be 1,
1.
right?
Hmm.
Because root 2 will get cancelled.
Yes, sir. That's what I told.
Okay. So this is how you can see the problems on balancing.